Hey y'all, what's up? My name is Eric, and this is my Lab 2 on projectile motion. So to begin, let's discuss some key fundamental physics principles. We obviously have Newton's second law, where F is equal to ma, and in this case, it's just F equal to mg. In addition, we have the drag force formula, which is equal to negative b v squared v hat. And to model the motion, we typically use the position and velocity update formulas, which are demonstrated here on the slide. And regarding motion, in the x direction, the velocity stays constant as long as there is no drag. But in the y direction, the velocity changes depending on if there's gravity or drag. So, the purpose of this experiment is to record the trajectory of a paper ball in both the x and y directions, and then compare that data to two computer models. And in one case, the computer model only accounts for gravity, whereas in the other case, it accounts for gravity and drag. So here's just a visual demonstration of the paper ball. Without drag, gravity is the only force acting upon the ball, which leads to the y velocity changing. But then with drag, alongside gravity, there's also a drag force which opposes the motion regardless of where the ball is going. So in this case, it's affecting the y velocity, but also the x velocity, meaning the x velocity is not constant. And in this case, the system would be the paper ball, where the surroundings would be gravity, drag, and typically just any forces that oppose motion. So here's just a picture of my tracker analysis that I used to record my ball. And as you can see, I used increments of t equals 0.033, and in the x direction, the displacement was constant. And based off this formula, the d equals v t, I was able to find the velocity of the x direction to be 0.9489 meters per second. And then again, using kinematics, using the peak height and using all the formulas and information given, I was able to find the velocity of y to be 1.5365 meters per second. All right, so here's just the computer model and simulations. This is the initial conditions I used, where the ball is 0.004 kilograms. That's the initial velocity, and then g is obviously equal to 9.8. And this is the model without drag. As you can see, um, it's a very smooth parabolic path. But in this case, where I put b is equal to 0.05, you see the path is very curved, and this is due to it resisting motion and just not cooperating, I guess we could say. And here's just the data graphed on on a graph. And as we can see, trajectory. So the experimental graph showed the highest height of 0.148 meters, as you can see, the blue line. And then gravity, like when you account for gravity, the peak height decreases to around zero point 0.1 meters. But then with gravity and drag, it significantly decreases to a number far less. And what does this show right here? It just shows that what's it called? As more forces are applied on the system, the trajectory overall is just weaker, and it just doesn't go as far. And now you might be wondering, well, Eric, why is there such a big difference? Well, there could be a multitude of reasons. One reason is I may have not accounted for like the initial launch force, like cause when I launched the ball, like there's obviously a force that had to be exerted, so I didn't really count for that. And secondly, that ties into human error. So like my timing on tracker, like I may have just like misplaced it by a couple milliseconds, which in this scenario, like every millisecond counts. And also, I may have just rounded like incorrectly at times. In addition, I kind of put b as 0.5, but like that could also like if I change the b value to trajectory on the y line, for example, it would change. So in regards to the lab, terminal velocity is just the idea when the net force is equal to zero. And based off this, my gravity plus drag model does predict terminal velocity, as the velocity typically levels off over time as drag, counteracts and eventually equals gravity. And then there is another interesting question to ponder on. It's as in which takes longer to land, a projectile thrown straight up, or the projectile I had right here, where it's thrown at an angle. So based off the data that I saw, it would be straight up, and this is because using the kinematic equation v equals a v naught minus gt, if you rearrange the formulas, two v naught over g for straight up and two v naught sine theta for over g for a projectile. And then if I use v naught is equal to 2 and theta is equal to 45, I would have a straight up time of 0.408 seconds and a projectile time of 0.288 seconds, meaning it would take longer to go straight up for the projectile. And that is my project and presentation. Thank you for listening, and I hope you have a great day.